Learning good views through intelligent galleries. The definition of a good view of a 3D scene is highly subjective and strongly depends on the scene content and the 3D application. Usually, camera placement is performed manually through two-dimensional visual interfaces on a try-and-error basis. This is a laborious task. For example, when setting cameras of every single keyframe of an animation. Defining good views turns out to be difficult, since there is no absolute best view. For example, the best view of a fluid simulation according to a computer artist, on the left, differs from the one of a fluid specialist. In this work we face the challenge of producing good 2D views by computer using the same approach as humans. Learning. The interface has 5 options: open, user selection, automatic selection, reproduction, and finalize. With a gallery interface, the user selects subjective good views from a selection of possible views. From the selected views, a new gallery is generated by genetic reproduction. Each view is characterized by a collection of descriptors, and the machine learns from the user selection his preferences. We use a formulation derived from SVM, support vector machine, which allows nonlinear classification of good views, here shown in red for the previous training on the cow. We improve the SVM technique by analyzing the contribution of each descriptor to the classification and setting the SVM parameters to optimize the use of each descriptor. Our technique learns from the user at each click, evolving with continuous usage. It is one of the first try to incorporate learning into design galleries. The trained machine can automatically order and select good views for similar models. In particular, we guide the user by putting the best view at privileged positions in the gallery. The user can repeat the manual or automatic selection with gallery reproduction until converging to a satisfactory final view. Here we show the results of training from the side view of the cow model and automatically place the camera for other similar models. We compare our technique with previous work that use a single descriptor. We use a single training on Max Planck and David head models. Our technique is able to learn complex rules from a simple interaction. For example, training on a simple trefoil knot leads to good automatic selection for complex knots. Our technique is able to handle complex depth seen with occlusion. For example, on randomly generated forests, with a partially occluded dinosaur, a single training leads to a good tracking of the dinosaur's front. In the battle scene, only the first and last frames were trained. Thank you for your attention.